Welcome to this video on using generating functions to solve recurrence relations. We're going to look at a simple recurrence relation and use generating functions to find a formula for the sequence. And even though this is a simple example, it does feature all of the techniques that we typically encounter when we're solving these recurrence relations with generating functions. So here's our recurrence that we want to solve. We know that a0 is equal to 0, and we know that an plus 1 is equal to 2 times the previous term plus 1. And this recurrence holds for n greater than or equal to 0. So the first thing we should do is just calculate the first few terms, and the sequence that pops up is 0, 1, 3, 7, 15, 31, and so on. This is a pretty recognizable sequence. It's just one less than the powers of 2, and so we would conjecture that the formula that we're looking for is that a of n is equal to the n minus 1. And I'm not saying that one should use generating functions to solve this. Actually, induction would solve this problem much faster. But the point of this video is to show you the generating function techniques that we can employ to solve these recurrence relations, and that will be really useful when we have unknown sequences that we can't just guess the answer to. So here's how we begin. We define our ordinary generating function, a of x, and that's equal to the sum as n goes from 0 to infinity of a n times x to the n. And now my first step to solving the recurrence is to convert it into an equation about this ordinary generating function a of x. So here's my recurrence. an plus 1 is equal to 2 times an plus 1, and that holds for n greater than or equal to 0. And the first thing I'm going to do is multiply both sides by x to the n. So there's an x to the n here and an x to n there. And so this one statement actually holds for an infinite number of cases, right, for every possible n. So what I'm going to do is create a simple equation that actually incorporates this infinite set of equations into one place. And we can do that by just summing them all up. We're summing over all n, so n goes from 0 to infinity, and here I have an plus 1 times x to the n. Over here I sum over the same amount, and I have 2an plus 1 times x to the n. Now the first thing I would like to do is I would love to turn this left-hand side into a of x, but there are a few things that I have to fix. The first one is that here we have an an plus 1, but the power of x is not n plus 1, it's x to the n. And so I want to fix that by multiplying by x over x, so that I'll pull one x inside to make it an x to the n plus 1, and I'll keep the 1 over x on the outside. Now a second thing that I notice is that this sum is missing the a0 term, right? This sum, if I plug in n equals 0, I get a1. And so here you see on the next line I have accounted for the fact that that a0 term is missing. Moreover, I've re-indexed. Instead of having this be x to the n plus 1, I write x to the k. So here k is equal to n plus 1. And I still have my 1 over x. I've got my minus a0. And now this is a sum that goes from 0 to infinity and in fact looks like my desired generating function a of x. Meanwhile, the right-hand side is a little more straightforward. I'm just going to split this out. I'll pull the 2 out front, and I have an an x to the n. And then I just have a very simple looking power series, the sum of x to the n, as n goes from 0 to infinity. Here's the formula from the bottom of the last slide, and now I want to start simplifying in any way I can. And the first thing that I'm going to do is I'm going to multiply both sides by x. So I'll multiply by an x here, I'll multiply by an x over here, and when I do that, what's left on the left-hand side is just a of x minus a0, because this infinite sum is just the ordinary generating function a of x. Then when I distribute this x out, I get a 2x. Here's another copy of a of x. So there my x goes to here. And this is a well-known power series. If I'm just summing x to the n from 0 to infinity, that's just 1 over 1 minus x, the geometric series. So now my task is to get all of the appearances of a of x onto one side. So I do that by subtracting the 2x times ax from both the left and right-hand sides. And I'm also going to substitute in the value for a0, that's just 0. My formula simplifies to this. After dividing both sides by 1 minus 2x, I actually get the generating function for this sequence a0, a1, up to an, and so on. And so if someone asked me to solve for the generating function, I would just be done. I could hand them this function and say, this is the function that will give you the sequence that satisfies the original recurrence. In our case, we want to find the individual values of a sub n, and so we need to keep going. And this is where we will employ something called partial fractions. So here we have a function a that's a rational function, so it's something on top, and it's a bunch of linear terms multiplied together on the bottom. It turns out that I can always separate this fraction on the right-hand side into two simpler functions. In this case, it's c over 1 minus x plus d over 1 minus 2x. And if this is really true, that means c times 1 minus 2x plus d times 1 minus x is going to give me the original numerator. That original numerator is 0 plus x. And so I actually have two equations in two unknowns. We can solve them. We get c plus d equals 0 and minus 2c minus d equals 1. And we find that c is equal to minus 1, d is equal to 1. And that means that I can separate out my generating function into two rational functions, minus 1 over 1 minus x plus 1 over 1 minus 2x. And each of these rational functions is a simple one that we can find the power series for. Here's our generating function formula. We split it into two simple rational functions that we can apply the geometric series to. The first one, 1 over 1 minus x, is just the sum of x to the n. And the second one is very similar. I'll just do a u substitution. If I take u to be equal to 2x, then the second part has the form 1 over 1 minus u. Okay, so the power series for that is just u to the n, or 2x to the n. And when I distribute out that n, I get 2 to the n times x to the n. And then my next job is to actually combine these two infinite series into one. And then I find that the coefficient of the x to the n term is in fact 2 to the n minus 1. Now this is our generating function a, which of course is just the sum of a and x to the n. And so what I conclude is that a n is equal to 2 to the n minus 1. So that's a long calculation, but each of the individual steps is pretty straightforward. Let me summarize what I did. So let's say you have a recurrence relation for some series an, and you want to solve it. Well, one way to do that is to create the ordinary generating function where we sum over a and x to the n. And I'll take that recurrence relation and I'll multiply both sides of it by x to the n. And I sum over all the possible values of n. So wherever that recurrence starts, that will be my lower bound, and I go up to infinity. The next thing I do is I want to simplify what I have. So my goal at this point is to find copies of the ordinary generating function a of x. But here you have to be really, really careful. One thing is you may have to reindex. And the other thing that happens is we're often missing some first terms. This depends upon where the recurrence starts. If the recurrence doesn't start until 2, then you might be missing the a0 and the a1x terms. So you need to account for the fact that they're missing. You'll have to write a of x minus a0, or maybe a of x minus a0 minus a1x, and so on. But okay, let's say you've done that. Now we have a bunch of appearances of the ordinary generating function, as well as some other algebraic terms. You now need to look at the other power series that you see and hopefully recognize them and replace them with the appropriate formulas. Things like the sum of x to the n is 1 over 1 minus x. Finally, you'll rearrange and solve so that you have a of x on one side, and that now gives you the ordinary generating function. Congratulations. Finally, if you're asked to actually find a formula for each of the a n terms, you're going to have to use some known power series to take the algebraic expression that you see for a of x, break it into pieces, and find the power series for each of those pieces. And one common technique for this is partial fractions, and we showed you an example of how that worked. I do admit that you really have to pay attention to what you're doing. Any small algebraic error you make will have dire consequences. So do this slowly, check your work, compare your answer with a friend, and I promise that the more times you do this, the better you get at it. So that's it for this techniques video. I will see you in the next one.